Hello all, welcome back to our channel, Ecotech Fusion Intelligent Ideas Next Generation. This is Series 20. Come let's go into the video. The first topic for today is delivery robot with person verification via mobile authentication and face matching. So here the project proposes the design and implementation of an autonomous delivery robot capable of securely delivering packages by verifying the recipient's identity using two-step authentication, that is mobile-based or token, QR code authentication and face recognition based identity verification at the delivery point. The robot navigates autonomously using GPS and obstacle avoidance sensor, maybe like ultrasonic or LiDAR sensors, and upon reaching the delivery location, it requests the user to scan the mobile generated QR or OTP code and performs the real-time face matching with stored data to verify the connect recipients before releasing the package. Moving on to the innovation highlights, dual authentication system. So it combines a mobile token, that is either OTP or QR, with face recognition to ensure secure handover of deliveries. Next, autonomous navigation. It uses path planning, GPS and obstacle avoidance to move independently in controlled environments like campuses, apartment or gated communities. Real-time face recognition. It employs CNN-based models, says FaceNet or mobile FaceNet, optimized for onboard processing using edge devices like Nano or Raspberry Pi. Smart lock mechanism. This delivers the package only after successful multi-factor verification, enhancing security against theft or impersonation. Remote monitoring and alerts. It sends alerts to admin in case of authentication failure, unusual behavior or blocked navigation paths. Finally, privacy compliant device. So here all biometric data is stored encrypted locally or handled via a secure cloud backend, ensuring compliance with data protection laws. Moving on to the future scope, urban and last mile logistic integration. So it extends the system to urban settings for last mile e-commerce delivery, especially during off hours or peak hours. Multi-person face recognition. So it adds group identity verification, say for example, delivering to offices or any institutions using multi-face detection algorithm. Then drone plus ground robot hybrid system. So it combines ground bots with drones for air-ground collaborative delivery to handle stairs, rooftops or remote terrains. Next is AI-powered route optimization. So it integrates deep enforcement learning or graph-based algorithm to optimize delivery schedules and paths dynamically. Voice interaction and feedback. It adds voice command recognition for better interaction with user and voice alerts in case of delivery failure. Fleet management system. It develops a centralized dashboard for managing multiple delivery robots or multiple delivery bots, real-time tracking and analytics. Finally, integration with e-commerce platform. That is, it connects with apps like Amazon, Flipkart, or any local delivery system for seamless AI-powered automated delivery. Moving on to the second topic for today, physics-guided color space transformation for robust underwater image recovery. So here the project focuses on enhancing underwater images by integrating physics-based light absorption and scattering models with adaptive color space transformation. So here in underwater environments, colors get distorted due to wavelength dependent attenuation, that is red light disappears first followed by green and blue, resulting in low contrast color shift and haze in images. And then this technique applies a physics-aware correction model that estimates the water depth, backscatter and ambient light properties and uses them to guide adaptive color space transformation, say for example from RGB to a modified HSI or CIE lab. This allows for more accurate restoration of true colors while preserving the edges and structural details. Moving on to the innovation highlights, Yes, physics-based degradation modeling. So here it uses the light propagation model considering wavelength-dependent absorption and scattering effects to estimate image distortion factor. Color space optimization. So this transforms the image into a customized color space where enhanced operations like contrast stretching, dynamic range compression, and white balancing are more effective. Depth awareness. It incorporates depth map estimation, say possibly from stereo images or monocular cues, to apply depth-specific correction for better realism. Next is edge and texture preservation. It utilizes guide filtering or bilateral filtering techniques that preserve edges while reducing noise in enhanced steps. Real-time potential. So optimized for execution on GPUs or edge AI hardware like Jetson Nano or Coral TPU, enabling near real-time underwater video enhancement. Moving on to the future scope, integration with autonomous underwater vehicles. So here enhancement systems can be integrated into AUI vision modules to improve object detection and navigation accuracy. Marine biology and habitat monitoring. So clearer imagery supports better identification of coral bleaching, fish species, and underwater pollution levels. Next is augmented reality for drivers. So here, the enhanced real-time feed could support AR overlays for diver navigation and exploration assistant. Hybrid deep learning modules. Future versions may combine the physics-guided pipeline with GANs or transformer-based modules or models for further realism and robustness. Multispectral enhancement fusion. This extends the system to fuse visible and near-infrared or sonar-based data for underwater enhancement in extreme turbidity. Cloud and ECE for environmental mapping. Yes, the data from the system can be synchronized with the cloud platform for building long-term maps of underwater ecosystem and structures. Moving on to the third topic for today, smart greenhouse monitoring system with AI-based pest detection and automated climate control. So here, the project presents a very smart greenhouse system that leverages AI and IoT technologies to monitor and control key environmental parameters such as temperature, humidity, soil moisture, and light, while integrating a vision-based pest detection system using deep learning. Here, the sensor collects the real-time environmental data, which is used to automatically control fans, irrigation, ventilation, and lighting systems via actuators. Simultaneously, a camera module monitors plants and detects the pest infections or anomalies in foliage using trained convolution neural networks or YOLO-based object detection model. Finally, the system can be accessed and managed via a mobile or web interface, offering farmers live analytics, predictive alerts, and intelligent control, ensuring optimal plant growth and reduced crop losses. Moving on to the innovation highlights, AI-based pest detection. So here, it implements deep learning models to identify common pest or disease patterns on plant disease in real time. Automated climate control. It uses sensor feedback to dynamically adjust environmental condition through actuators, controlling fan, shade panels, and heaters. IoT cloud synchronization. Here, the real-time data is synced to a cloud platform for analytics, remote monitoring, and AI model updates. Low-cost hardware compatibility. Here, it is designed using Raspberry Pi or ESP32 cameras and affordable sensors to make the system cost-effective for small and medium greenhouses. Predictive alerts and automation. So here the machine learning algorithms forecast temperature and humidity trends, optimizing energy and water usage. User interface. Here the simple dashboard for farmers to control and view greenhouse status remotely via smartphone or PC. Moving on to the future scope, drone integration. Here the AI-powered drones for aerial pest inspection and targeted pesticide spraying. Next is multispectral imaging. So here it incorporates spectral cameras for more accurate plant health analysis and stress detection. Scalable cloud AI. This deploys scalable machine learning services to manage multiple greenhouses across region. Next is voice control and local language support. It implements voice assist control with regional language support to aid farmers with limited technical knowledge. And then autonomous farming bots. So add a robotic system for planting, harvesting and maintaining greenhouse carts based on AI instruction. Blockchain for data integrity. Use blockchain to secure sensor and AI data for traceability in organic farming certification. Moving on to the last topic for today, swarm of autonomous water monitoring boats for scalable environmental surveillance. So here the project proposes the development of a swarm of autonomous water monitoring boats, small AI-powered vessels equipped with water quality sensors, GPS and communication modules. So here the boats operate collaboratively across large water bodies like lakes, rivers, reservoirs to collect and transmit the environmental data such as pH, turbidity, temperature, TDS, dissolved oxygen and contaminants. The swarm leverages multi-agent coordination algorithm to divide and conquer the area of interest, reducing data collection time and increasing spatial resolution. The boats communicate using LoRa, Wi-Fi mesh or 5G networks and feed data to a central server or cloud platform for real-time monitoring, analysis and visualization. Moving on to the innovation highlights. Swarm intelligence. So here it implements distributed AI for coordinated among bots, enabling them to explore, monitor and avoid overlap autonomously. Multi-parameter water quality sensing. Here each unit carries modular sensors to monitor key water quality indicators with high spatial granularity. Next is self-organizing navigation. It uses GPS plus AI-based path planning and obstacle avoidance to adaptively map large or dynamic water areas. Next is real-time cloud integration. Sensor data is transmitted and visualized on a centralized dashboard using cloud platform like ThinkSpeak, AWS IoT or Blink. Energy efficiency. Boats are powered by solar panels with battery backup, enabling long-duration autonomous operation. Modular and scalable architecture. Here the system supports easy addition or removal of boats, ideal for scaling up or targeting specific environmental events. Moving on to the future scope, AI-based anomaly detection. So here it trains EML models to detect unusual patterns, say for example sudden pH drop that indicates industrial discharge or contamination. Autonomous docking and charging station. So it integrates with self-charging docks to allow 24/7 monitoring with minimal human intervention. Swarm drones plus boats collaboration. So here it combines aerial drone surveillance with water swarms for comprehensive 3D environmental mapping. Satellite data integration. This fuse ground truth data with satellite imagery for large-scale environmental modeling and trend analysis. Citizen science integration. It opens the data to local communities or NGOs through apps or dashboards for transparency and awareness. Disaster response use case. So here it deploys a system post-flood or chemical spill for real-time water quality assessment in inaccessible zones. Hope you are interested to know more about creative ideas that helps you in different aspects. Please stay tuned for more information. Thank you.